What if you could understand the entire universe in under an hour? It sounds like an impossible task, a journey too vast to begin. But the truth is, the fundamental rules that govern everything from the smallest subatomic particle to the largest galactic supercluster are all part of one unified story. That story is physics, the very language of reality. Today, we will embark on a grand tour of this incredible subject. We are going to break down every major branch of physics clearly, visually, and powerfully. Our goal is to connect the dots to reveal the elegant tapestry that weaves together motion, energy, light, and even the fabric of spacetime itself. Whether you're a student cramming for an exam, a curious mind seeking to grasp the world around you, or simply someone who has always wanted to finally get physics, this is your shortcut to the cosmos. So, let's begin. 1. Classical mechanics. Our journey starts where physics itself began its modern life, with the predictable, tangible world of classical mechanics. Before the 17th century, the motion of objects was a subject of philosophical debate, shrouded in mystery. Then, Sir Isaac Newton gave us a set of simple, yet profoundly powerful, laws that described how and why things move. These laws were revolutionary because they were universal. The same force that causes an apple to fall from a tree is what keeps the moon in orbit around the Earth. The core principle can be distilled into a beautifully simple equation: force equals mass times acceleration, or F equals ma. This single line of mathematics gives us the power to predict the trajectory of a baseball, design the perfect roller coaster loop, and even plot the course of a spacecraft to Mars. It describes a world of cause and effect, where every motion is the result of a force, every action has an equal and opposite reaction, and an object in motion stays in motion. Classical mechanics built the modern world, from the gears in a clock to the bridges that span our rivers. It is the physics of our everyday experience, a deterministic and reassuringly solid foundation upon which everything else is built. 2. Thermodynamics and energy. From the clockwork precision of mechanics, we move to the seemingly chaotic, yet equally rule-bound, realm of thermodynamics and energy. This is the science of heat, work, and the flow of energy that drives everything from a steam engine to the metabolic processes in our own cells. At its heart are the laws of thermodynamics, which are some of the most fundamental and inescapable principles in the entire universe. The first law is a statement of conservation. Energy cannot be created or destroyed, only converted from one form to another. The energy in the food you eat is transformed into the kinetic energy of your movement and the heat that keeps your body warm. The second law, however, introduces a concept that gives time its arrow: entropy. It states that in any isolated system, the total amount of disorder, or entropy, will always increase over time. A pristine ice cube will inevitably melt into a disorganized puddle of water. A hot cup of coffee will always cool down, dispersing its heat into the room. This inexorable march towards disorder is why perpetual motion machines are impossible and why the universe itself is constantly evolving. Thermodynamics explains why stars shine, why engines work, and why life itself is a constant, uphill battle against the relentless pull of entropy. It is the science of change and transformation. 3. Electromagnetism. Now, let's illuminate another fundamental force: electromagnetism. For centuries, electricity and magnetism were seen as two separate, curious phenomena. Electricity was the crackle of lightning and the static shock from a wool blanket. Magnetism was the mysterious pull of a lodestone on iron, but in the 19th century, scientists like Michael Faraday and, most notably, James Clerk Maxwell discovered they were two sides of the same coin. Maxwell's equations, a set of elegant mathematical statements, unified them forever. They revealed that a changing electric field creates a magnetic field, and a changing magnetic field creates an electric field. This beautiful, self-perpetuating dance gives rise to an electromagnetic wave. And what is this wave? It's light. Radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays are all just different frequencies of the same phenomenon. This revelation was one of the greatest unifications in scientific history. It not only explained the nature of light, but also paved the way for every piece of modern technology that relies on it, from our smartphones and Wi-Fi routers to medical imaging and solar panels. Electromagnetism is the force that binds atoms together, powers our civilization, and allows us to see the world. 4. Quantum mechanics. As we journey deeper, the familiar, intuitive world begins to dissolve. We now enter the strange and counterintuitive domain of quantum mechanics. At the turn of the 20th century, physicists discovered that the classical rules of Newton simply broke down at the atomic and subatomic scales. The universe, at its most fundamental level, is not a collection of tiny, solid billiard balls. Instead, particles like electrons and photons exhibit a bizarre wave-particle duality, behaving like a particle in some experiments and like a wave in others. This is most famously demonstrated in the double-slit experiment, where a single particle seems to pass through both slits at once, interfering with itself like a wave. This quantum world is governed by probability, not certainty. We can no longer know everything about a particle with perfect precision. This is enshrined in Werner Heisenberg's uncertainty principle, which states that the more precisely you know a particle's position, the less precisely you can know its momentum, and vice versa. There is a fundamental fuzziness built into the fabric of reality. This strangeness allows for phenomena like quantum tunneling, where a particle can pass through a barrier it classically shouldn't have enough energy to overcome, a process essential for nuclear fusion in the Sun. Quantum mechanics may seem esoteric, but it is the foundation of modern electronics, from the transistors in your computer to the lasers in a Blu-ray player. It is a world of probabilities, paradoxes, and profound mystery. 5. Relativity. Having explored the incredibly small, we now turn our gaze to the incredibly large and fast with Albert Einstein's theories of relativity. Just as quantum mechanics revolutionized our understanding of the small, relativity shattered our classical notions of space and time. Einstein's special relativity, born from the observation that the speed of light is constant for all observers, revealed that space and time are not absolute. They are interwoven into a single four-dimensional fabric called spacetime. For an object moving at very high speeds, time itself slows down and its length contracts in the direction of motion. This isn't a trick of perception, it's a real, measurable effect known as time dilation. 10 years later, Einstein expanded this into his theory of general relativity, which presented a new and radical picture of gravity. He proposed that gravity is not a force pulling objects together, but a curvature in the fabric of spacetime caused by the presence of mass and energy. Massive objects, like planets and stars, create a gravity well, a dip in spacetime that other objects then follow. This is why planets orbit the Sun. They are simply following the straightest possible path through curved space. General relativity predicts the existence of black holes, regions of spacetime so warped that not even light can escape, and the bending of starlight around massive objects. It's not just an abstract theory. The GPS in your phone must account for both special and general relativistic effects to give you an accurate location. Relativity tells us that the stage on which the universe plays out is not fixed but dynamic, flexible, and shaped by its contents. 6. Nuclear and particle physics. Our penultimate chapter brings us back down to the building blocks of matter itself, into the world of nuclear and particle physics. What are we and the world around us truly made of? We know that matter is composed of atoms, which have a dense central nucleus of protons and neutrons surrounded by a cloud of electrons. But what are protons and neutrons made of? Particle physics probes this question by smashing particles together at near light speeds and massive accelerators. These collisions have revealed a veritable zoo of fundamental particles, all neatly organized into what is called the Standard Model of Particle Physics. This model describes the 17 known fundamental particles, the quarks that make up protons and neutrons, the leptons which include the electron, and the bosons that carry the fundamental forces. It includes the famous Higgs boson, the particle associated with a universal energy field that gives other fundamental particles their mass. This field of physics explains the immense energy released in nuclear reactions, both in the fission that powers nuclear reactors and the fusion that powers the sun and stars. It is a quest to find the most elementary ingredients of reality, a journey to the very heart of matter. 7. Cosmology and unified theories. Finally, we arrive at the frontier where all these branches of physics converge, cosmology and the search for a unified theory. Cosmology is the study of the origin, evolution, and ultimate fate of the universe as a whole. The prevailing theory is the Big Bang, which posits that our universe began approximately 13.8 billion years ago from an incredibly hot, dense state and has been expanding and cooling ever since. But this grand narrative is incomplete. Observations show that galaxies are spinning faster than they should, held together by an unseen gravitational influence we call dark matter. Furthermore, the expansion of the universe is accelerating, driven by a mysterious force we've named dark energy. Together, these two enigmatic components make up about 95% of the universe's total energy density, leaving the ordinary matter we've been studying, the stuff of stars, planets, and people, as a mere 5%. The ultimate goal of physics is to find a single, all-encompassing theory, a theory of everything, that can unite the laws of the large general relativity with the laws of the small quantum mechanics. This is the Holy Grail. Theories like string theory, which suggests that all fundamental particles are just different vibrations of tiny, one-dimensional strings, are promising candidates, but they remain unproven. This final chapter is about the biggest questions we can ask. Where did it all come from? What is it made of, and where is it all going? Summary. We have traveled from the falling apple to the expanding cosmos, from the deterministic world of Newton to the probabilistic realm of the quantum. We've seen how energy flows, how light travels, and how mass warps the very fabric of existence. It's a story of unification, of seeing disparate phenomena as different facets of a deeper, more elegant reality. This journey through physics is more than just an academic exercise. It's a fundamental part of the human story, our unending quest to understand our place in the universe. Because in the end, the iron in your blood, the calcium in your bones, and the oxygen you breathe were all forged in the hearts of dying stars billions of years ago. The laws that govern the furthest quasar also govern the firing of neurons in your brain. Physics doesn't just explain the universe, it explains you.